Okay, AP Statistics fans, our topic for today is expanding binomials in Pascal's triangle. This is something that you may have seen in Algebra 2 or you may have seen it in pre-calculus, but what I'm doing is kind of introducing where Pascal's triangle comes from and this concept of binomials. So even though we're not going to have to expand binomials in AP Statistics, I just want to show you where the numbers and the values are coming from. Before we start, let me give you your joke of the day. Two antennas got married. The ceremony wasn't much, but the reception was excellent. Antenna, reception. Okay, so we're going to start where we just look at basically some patterns here. So if I say a plus b, and I raise that to the first power, well, that's a plus b. Okay, it's 1a plus 1b. If I take a plus b raised to the second power, that means that we take a plus b and we multiply it by itself. And if we go ahead and double distribute, or you may have learned this as FOIL, we get a squared plus 1ab plus, that's also 1ab plus b squared. And we get a squared plus 2ab plus b squared for that. Okay, and one thing I'm going to do is I'm going to highlight the coefficients here. So 1a squared, 2ab, 1b squared. If we take a plus b and now we want to raise it to the third power, there are a couple ways we can look at this. I could say that's a plus b times a plus b raised to the second. Using the laws of exponents, that's still a plus b to the third power. Since we already did a plus b to the second, we got this. So it's a plus b times a squared plus 2ab plus b squared. So this time when I distribute, a to the third plus 2, a times a is a squared, and then b plus a times b squared, and then I distribute the b here, I'll write that as a squared b plus, that would be 2a, and then b times b is b squared, and then b times b to the second, we add the exponents, that's b to the third. Now we do have some like terms here. We have 2a squared b and 1a squared b. We also have ab squared, that's 1, and 2ab squared. So we end up with a to the third plus, if we add the a squared b's, we get 3a squared b. This is 3ab squared, and this is 1b to the third. So there's 1, 3, 3, 1. Now, if you are familiar with Pascal's triangle, then some of these values are starting to look familiar to you. One thing that I didn't do this, but we could have said a plus b to the 0. Anything raised to the 0 is always equal to 1. Okay? Now, we could keep going with this. We could keep expanding and multiplying this out, but at this point we have enough to say there are some definite patterns that are going on here. When we look at these values, when we look at the coefficients, they fit a pattern called Pascal's triangle, where the first number is a 1 in the first row, and then the second row is 1, 1. The third row is 1, 2, 1. The fourth row is 1, 3, 3, 1. Now that happens to be the coefficients that we just got from a plus b to the 0, a plus b to the first, right? That's 1a and 1b, 1, 1. A plus b raised to the second, we had 1a squared plus 2ab plus 1b squared, 1, 2, 1. And then here's a plus b to the third. 1, 3, 3, 1. Now, if we wanted to keep going here, if we want to do a plus b to the fourth, notice that it's getting longer and longer to multiply this out, but if we realize the pattern, the way that we continue with Pascal's triangle, we always start with the number 1, we always finish with the number 1. Now the numbers in between we get from adding the two numbers that are above. So if I take 1 and 3, that's 4. If I add 3 and 3, I get 6. And if I take 3 and 1, I get 4. 1, 4, 6, 4, 1. So I could write the answer to a plus b raised to the fourth. Now one other thing about this, I'll go to the a plus b raised to the third. So notice the pattern with the exponents. First of all, with the a's. A to the third, a to the second, a to the first. Now there's no a there because that's a to the 0. So the exponents for a are decreasing one at a time. But for b, now there's no b here because that's b raised to the 0, b raised to the first, b raised to the second, b raised to the third. So the second variable, the exponents are increasing by 1. Now we can use that pattern here where the first coefficient is 1. Now it would be a raised to the fourth and then b raised to the 0, which again is just 1. We normally wouldn't write that. Plus 4, a raised to the third. So the exponent for a is going to keep decreasing by 1. The exponent for b will increase by 1. So that's b to the first. And then 6, the coefficient is 6. A to the second, b to the second, plus 4, a to the first, b to the third, plus 1, a to the 0, which is just 1, b to the fourth. So Pascal's triangle can make this nice if we know the patterns and how they're represented. If we kept going, if we go one more row here, this would be 5. 4 plus 6 is 10. 10, 5, 1. If you don't believe me that these are going to be the coefficients, you can multiply out a plus b to the fifth. But I guarantee you these are going to be the coefficients for that. So this is a really nice pattern. The problem with this pattern is that if I asked you to do a plus b to the 12th, well, I mean, do you want to go out to 12 rows? We're up to 5. We're up to a plus b to the 5th. We'd have to go through this 7 more times, which, to be honest, is going to be a lot of work. So if we can find some patterns to this, that would be really nice. And there is some other patterns involved. These numbers, I'll take this row right here. If you think back to the idea of combinations and permutations. Now I have a set of notes, a different set of notes that actually addresses what these are and how to calculate them. For us, we are going to be using combinations. And the formula for a combination is if we have n objects taken r at a time, that is n factorial divided by r factorial times n minus r factorial. Now, again, if you don't know what factorial is, you'd have to go and look that up. Okay, that's not the most important part of this. The idea is that a combination will get us these values. So the number 1 here, now this is the 5th row. So if I take 5 objects and I choose 5 of them, and if I work that out, I would get 5 factorial divided by 5 factorial times 5 minus 5 factorial. This is equal to 120. and that's 120 times 1. 0 factorial is actually 1, and so the answer here is 1. Now, nicely for us, if you don't want to go through that work all the time, is I could say 5, hit the math button. Here, let me show you here. 5, and then here's math. Go over to probability at the top, and NCR means combination. So if I want to choose 5 of those, I would get, there's my value 1. What if I wanted to do 5, choose 4? What about 5, choose 3? Now, do you notice anything about the numbers that we're getting? 1, 5, 10, 1, 5, 10. So that's 5, choose 5. Whoops. 5, choose 5. This would be if we have 5 objects and we choose 4 of them. This would be 5, choose 3. This would be 5, choose 2. This would be 5, choose 1, combination, 5, choose 1. And this would be 5, choose 0 for that. And the way that I'm reading this here, for example, is 5 objects, but we choose 4 of them. How many ways can we choose 4 out of 5? How many ways can we choose 3 objects out of 5? How many ways can we choose 2 out of 5? And it's equal to these values in Pascal's triangle. Okay, so the really cool thing here is that we can calculate, we can expand binomials using this knowledge. Now, to generalize, if we wanted to do a plus b raised to the nth power. Now, n could be anything. It could be 20, it could be 35, it could be 11. The idea is that we'll start with n, choose n, a raised to that number n, b raised to the 0, plus n choose n minus 1, a raised to the n minus 1, b raised to the first, plus n choose n minus 2, a raised to the n minus 2, b squared. Now eventually we would get to the point where it would be n choose 1. That would be a to the first, b to the n minus 1, and then finally n choose 0, a to the 0, b to the n. Now I'm actually writing this backwards from the way that you would normally see it in the book. Normally they would start with n choose 0. They would start with here. I'm doing this for a very specific reason. You'll see that in the next set of notes. But if I asked you to expand, okay, here's the last thing here. A plus b to the 7th. Now again, I mean, this is going to be quite a bit of work. There's still a lot of writing. But it would be 7 choose 7, a to the 7th, b to the 0, plus 7 choose 6, a to the 6th, b to the 1st. The exponents for a will decrease by 1. The exponents for b will increase by 1. Plus 7 choose 5, a to the 5th, I don't need the parentheses, but I wrote it, b squared, plus 7 choose 4, a to the 4th, b to the whatever's left over, 7 minus 4 is 3. And notice that these exponents add up to 1 each time. Or I'm sorry, add up to 7, which is what the overall n value is. Plus 7 choose 5, a to the 5th, sorry, a to the 3rd, I'm going down. 7, 4, this should be 7, 3, sorry about that. A to the 3rd, b to the 4th. And we keep going. Okay, so I would be able to work this out And I would have 7, choose 7 is 1. So I would get a raised to the 7th power, b to the 0 is 1. This would be 7, a to the 6th, b. Now this, I think, is 21. Let me check. So if I want to do 7 objects and I choose 5 of them, 21, good for me. So that would be 21, a raised to the 5th, b raised to the 2nd, and so on. Okay, so I could multiply this out without having to go through this process here, which would take a very long time. So I'm using the idea of what's called the binomial theorem. Now, how this applies to AP statistics is going to come up in the next video. And that is the end.